Okay, this is so welcome to our third learning target. This is expected value in the arithmetic mean. So the point of this is actually I just want to make sure that students can articulate what the expected value is. So that's what we're going to work on today, and how the expected value relates to the arithmetic mean. So here's like a warm-up question. This question is just intended to get you to think about how to the expected value formula and how it can work, and just to look at how it relates to the average. So the following formula describes the expected value, the outcomes of a game, what might be the outcomes, and the probabilities. Write the equivalent expression as a series of numbers divided by a suitable number of trials. And we call that the arithmetic average. Okay, so a lot like we had with the spinner and Plinko, there were a certain number of trials, and so we want to kind of relate it to that. What I want students to be able to do is to explain how the expected value the sum of xp of x is related to the arithmetic mean, or how it's the same thing. So you can pause it and think about it. Okay, so in this case, your number of outcomes is 4. There's 4 different outcomes here, and the outcomes are 20, 40, 10, and 5. So that could be $20, $40, $10, and $5. Your probability is 0.1, 0.3, 0.2, 0.4. And so now the question becomes, now that we've kind of figured out what the probabilities are, and you can see those are the probabilities. This is the total number of outcomes. These all add up to 100%. So now we can ask ourselves, okay, well, what does this mean? And how many trials do you have? And so you want to think about how many, if we want to look at this as what you expect, how many trials are you looking at? And so there's 2 answers that are very simple with these formulas. You can either use 100 and look at this as 10 times out of 100, or you can use it as 10. And 10 is actually probably an easier example. You look at the 20 coming up 1 out of 10, the 40 coming up 3 out of 10, 2 out of 10, and 4 out of 10 for the 5. And if that's what we expect, we can actually calculate the average. This is going to be the expected value, x times p of x, and add them all up. But we can also calculate the average the exact same way by adding up 120, 3 40s, 2 10s, and 4 5s, and just divide them by 10. Now that'll get you the exact same thing. Okay, and so this is what I want students to be able to do, is to be able to identify that the sum of xp of x in a chart like this is the exact same thing as the arithmetic average. Now we usually see the chart vertically, not horizontally, but that's fine. I just did it that way so it would fit on the slide, really. Learning target. I know that the method for calculating expected value using the formula in the chart, so the sum of xp of x, is the same thing as taking the average of the expected number of n trials. I can explain this using a simple example. N trials maybe not the best example. N of s trials is what we're going to see. So recall the sum of the 2 dice. What would be a reasonable number of trials that could be used to distribute the frequency of each outcome? And so if we think about the spinner as 360 trials, we think about what we just saw as 10 trials. If we had the sum of 2 dice, we think about how many trials would it be to say, okay, I expect this many of this one, expect this many of this one. And so the answer is that n of s, 36. What would the frequencies be? So for each one, how many 2s would we have? We'd have 1. There's 2 3s, 2 ways to roll 3 out of 36. There's 3 4s, 4 5s, 5 6s, 6 7s, 5 8s, 4 3 2, and then 1 12. And the average outcome would be we would count 1 2, 2 3s, 3 4s, 4 5s, and similar until we get to 30, So we get actually 36 numbers here. There's 2 3s, 3 4s, and so on, all the way up to 12, and we divide those by 36, and that's the average. So that's actually, it's the same as the expected value. That's the average. We get the same thing as if we did actually a P of X column here. These are not P of X, but if we divided all these by 36 and then made an X P of X column, we would actually, and added them all up, we'd actually get the exact same thing. So the mean is 252 over 36, which is 7. That's what we'd expect to get, is a 7. For every number bigger than 7 we roll a number smaller than 7. Consider the distribution of heads if you flip 3 coins. Show that the arithmetic mean of what we would expect in 8 trials is the same as the sum of x p of x. So this is just kind of working through an example completely. So if we ask ourselves, like, what's the different things that can happen for the number of heads if you flip 3 coins? You could flip 0 heads, 1 head, 2 heads, or 3 heads. The probabilities are all out of 8. There's one way to flip no heads. You could draw a tree diagram to see that. It's just tail, tail, tail. There's 3 ways to flip 1 head. You could do head, tail, tail, or tail, head, tail, or tail, tail, head. 3 ways to flip 2 heads. That's similar to the first one, or to the last one, except instead of one head, it's 1 tail. And there's only 1 way to flip 3. It's head, head, head. Okay. And if we multiply the probabilities together, or the outcome by the probability, 0 times 1/8, and so on, we add them up, we get 1.5. Okay. And so that's actually how to calculate the expected value, is to do the sum of x p of x. That's what this is, sum of x p of x. The arithmetic mean, so the average, arithmetic average, is, well, we're going to have 1 0, 3 1s, 3 2s, and 1 3, and it's all divided by 8. And if we add that up, we get the exact same thing, 12 divided by 8, which is 1.5. So this really just shows that the arithmetic average of what we'd expect, so 1 0, 3 1s, 3 2s, and a 3, is the same as xp of x. So we're just highlighting that just by showing the work. Okay. So what I want you to articulate is just create your own example, one where it's not uniform, so one where the probabilities are different. Very simple example though. You can do it with like just 4 outcomes, and then just show this, that the arithmetic average of what we expect. And if you're wondering like how many trials do you use, you always use the n of s. So these are out of 8, so we're going to use 8. For the 36, we use 36. And just really write how many outcomes you have. You've got 1 0, 3 1s, 3 2s, and 1 3. And that's the distribution of the outcomes. So the expected number of heads and 3 flips is 1.5. What does that mean? It's an average, so every time you flip, so half the time you're going to flip 2 heads, half the time you're going to flip 1, maybe sometimes you flip none, but then that'll balance out with the sometimes you flip 3. Okay. These are some example questions that I'd ask you to do. Choosing 5 cards from a deck of cards. There's a lot of them, but how many trials would be appropriate to calculate arithmetic average of some distribution? It's not really like asking a question here, but if it was 5 cards from a deck of cards. Number 2, if you drew 2 cards with a deck from a deck with replacement, here the order has to matter because we are replacing it. So you ask yourself, how many ways can you do that? What would n of s be? Show the distribution of the number of spades you draw. Calculate the expected value by showing the arithmetic average and the table of values with the formula. So I want you to calculate the expected value in 2 ways. 3, that's really the mastery question. Create an example that demonstrates that the expected value calculated by using the formula is the same as the arithmetic mean of what you would expect with a suitable number of trials. So that's the question you really want to be able to explain. And page 159 is another deal or no deal question. Okay. I actually prepare the solutions here for number 1 and 2. So you can check to make sure you're on the right track, at least with number 1 and 2, if you look at the solutions.